Welcome to surface area examples. So recall for rotation about the x-axis, we had surface area was equal to the definite integral from a to b of f of x times the square root of 1 plus f prime of x squared dx. For rotation about the y-axis, we have surface area is equal to the definite integral from a to b of x times the square root of 1 plus f prime of x squared dx. So again, in both cases here, we are integrating with respect to x. The only change is whether our radius, oh, sorry, I forgot my 2 pi's. So we should have 2 pi times definite integral from a to b of x times the square root of 1 plus f prime of x squared, or 2 pi times the definite integral from a to b of f of x times 1 plus f prime of x, or times the square root of 1 plus f prime of x squared dx. So let's go ahead and just do a couple examples. So in our first example, let's find the surface area of the rotational solid formed by rotating the curve y equals x cubed on 0, 1 about the x-axis. So again, here we are looking at the curve y equals x cubed. We are looking between 0 and 1. And then we are rotating about the x-axis. So our graph we get kind of a horn shape. So when we do our surface area, we are looking at 2 pi times the definite integral from a to b, so from 0 to 1, of our f of x times the square root of 1 plus f prime of x squared dx. Our f of x here is x cubed. So that means that f prime of x is 3x squared. So we are looking at surface area is equal to 2 pi times the definite integral from 0 to 1 of x cubed times the square root of 1 plus 3x squared dx, otherwise known as 2 pi times the definite integral from 0 to 1 of x cubed times the square root of 1 plus 9x to the 4th dx. Now note, this is actually set up perfectly for u substitution. If we set u equal to 9x to the 4th, or just x to the 4th, or sorry, 1 plus 9x to the 4th. So if we set u equal to that 1 plus 9x to the 4th, then we have our du is 36x cubed dx So that means that x cubed dx is equal to 1 over 36 times du. We can convert our x's or not. So if we convert our bounds, we have x equals 0 would mean that u is equal to 1 plus 9 times 0 to the 4th, otherwise known as 1. X equals 1 will go to u equals 1 plus 9 times 1 to the 4th, otherwise known as 10. So we have our definite integral as 2 pi times the definite integral from 1 to 10 of, we just get square root of u, or u to the 1/2, times 1 over 36 du. Giving myself a little more space here. We have pi over 18. So this is equal to pi over 18 times u to the 1/2 would go to u to the 3/2. And then we would divide by 3/2. And we're evaluating at 1 and 10. So if we do a little simplification, this becomes pi over 18 times 2/3, or pi over 27 u to the 3/2, evaluated at 1 and 10. So we are looking at pi over 27 times, we're looking at the square root of 10 cubed, or the square root of 1000, minus 1. So we have pi over 27 times, in parentheses, the square root of 1000 minus 1. Let me update my screen. Again, we have pi over 27 times, in parentheses, the square root of 1000 minus 1. If we plug this into a calculator, we are looking at a total of about 3.56 units squared. Since we were talking about surface area. So this was rotation about the x-axis. Let's go ahead and do one more example where we rotate about the y-axis. So here we're finding the surface area of the rotational solid formed by rotating the curve y equals natural log of x on 1,4 about the y-axis. So just drawing our little picture here. Natural log x on 1,4. Then we're rotating about the y-axis. We are again taking our bands. We have our f of x is that natural log of x. F prime of x is therefore 1 over x. We have a is 1, b is 4. So we have that our surface area is equal to 2 pi times the definite interval from 1 to 4 of x times the square root of 1 plus f prime of x squared dx. So we are looking at 2 pi times the definite interval from 1 to 4 of x times the square root of 1 plus 1 over x squared dx. Let me update my screen. Throwing that x inside of our square root, this becomes 2 pi times the integral from 1 to 4 of the square root of x squared plus 1. X inside the square root becomes x squared, or sorry, x outside the square root becomes x squared inside the square root. And then we have our dx. This is one of our familiar trig substitution integrals. If you know it off the top of your head, you're welcome to just run with it. If you don't know it, you can always set up our trig sub. So running our trig substitution, we have our triangle. The addition inside our square root tells us that square root is our hypotenuse. So we have 1 plus x squared as our hypotenuse. X is opposite, 1 is adjacent. We have the tangent of x, sorry, tangent of theta is simply equal to x. So we have dx is secant squared theta d theta. Secant of theta is that square root 1 plus x squared. So we have that our integral of square root of 1 plus x squared dx is simply the integral of secant theta times secant squared of theta d theta. So we are looking at the integral of secant cubed theta d theta. Again, that is 1/2 secant theta tangent theta plus 1/2 times the natural log of the absolute value of secant theta plus tangent theta, and then plus c. If we go ahead and plug back in, so plugging in, let me update my screen one more time, I apologize. Plugging in the fact that tangent of theta was just x, and secant of theta was the square root of 1 plus x squared. And we are looking at the integral of the square root of 1 plus x squared dx is equal to 1/2 times the square root of 1 plus x squared times x plus 1/2 of the natural log, the absolute value of the square root of 1 plus x squared plus x and absolute value plus c. So we have then that our surface area is equal to we were looking at 2 times pi times the definite integral from 1 to 4 of the square root of 1 plus x squared dx. So this is 2 pi times 1/2 times x times the square root of 1 plus x squared plus 1/2 times the natural log of the absolute value of the square root of 1 plus x squared plus x and absolute value evaluated at 1 and 4. So we are looking at pi times 4 times the square root of 1 plus 4 squared is square root 17 plus pi times the natural log of the absolute value of the square root of 17 plus 4. And we are subtracting off pi times 1 times the square root of 2 plus pi times the natural log of the absolute value of the square root of 2 plus 1. If we go ahead and plug this into our calculator, we wind up getting approximately 51.18 units squared as our surface area. So that is surface area rotating about both the x-axis and the y-axis. In the next video, we will look at a very strange example where our curve goes on forever, and it turns out that it will have infinite surface area, but only finite volume.